you all have drinks, wine, and you had pizza. So my sole objective, really, in this part of the hour is to see how many of you I can keep awake. Let's see how I get on. My name's Ian Cooper. You can find my GitHub there. I'm iCooper on all the socials. I post less than I did. That says I'm old, and Dylan told you that earlier. He stole my thunder and said I've been running the .NET user group for 24 years. So I have been doing this a while. I've been doing messaging ever since in the late 90s. Late 90s is a really great period to be alive, by the way. Of all of human history, it's about the 5 years when things weren't shit. But my boss came to me basically, and he said...
Could we lose the lounge music, please? Whoever's playing the Lionel Richie.
Yeah, it's all right. I'm just doing the preamble anyway. My boss came to me and he dumped a manual on my desk. And he said, Ian, this is IBM MQ series. Some of our customers want to get it working. Good luck. And it was a typical IBM manual. It was utterly rubbish. It didn't tell you things like no matter what casing you used to type in the name of the queue, it would just turn it all to uppercase behind the scenes. This is so IBM could sell you their consultants and the tools that they had to actually make it work. But I worked with a guy called Marcus Rainbow, who knew a lot about messaging and a lot about Class A drugs too. But he knew a lot about messaging. I don't know the two are connected. And so I learned a lot, and I've been doing messaging ever since. And messaging is one of those things that I think it lies a little bit outside a lot of people's day-to-day. So they reach for HTTP and other tools. But it's really straightforward. And one of the ways when I run a whole 2-day workshop about messaging, one of the ways I talk about it is this, right? Messaging is just file transfer. It's pretty much just file transfer with some buttons and dials and knobs that you can turn to make that work, right? I will explain that a little bit when we talk about asynchronous, but yeah, so don't be frightened of it. I work on an open source framework for messaging for .NET. Any .NET developers in this room? That's a good job. And the rest of you, I don't know why you came. We just got V10 out. We've just discovered that Claude is pretty good at writing docs, which is lovely because no one likes writing docs. Wow, I think that must be CloudFront basically has died. Yeah, so V10 is out. Check us out if you want to. We talked about frameworks a bit at the end. There's a whole section on what frameworks you can use. There are others apparently, though why would you look for them? We'll start talking about being event-driven. We will talk about what that kind of means. How might I use events in an application? And then we'll talk about the two halves of the conversation in messaging, producers and consumers. Then I'll do some demos. They're going to be pre-canned. We're just going to roll ones that basically on video, save me to trying to connect to internet and figure out whether Azure is up. And then I'll talk about frameworks and middleware. Okay. The messaging rabbit hole goes very deep. We aren't going to go very deep, right? We're just going to actually sit in the room in the armchairs, and no one's going to offer you a chance to see how deep the rabbit hole goes. And part of the reason for that is I want you to understand the basic principles of messaging. You can get a long way into what complex messaging architectures look like, but we've got 1 hour, so let's steer clear of all that. It takes me 2 days to run a workshop, and I occasionally think you probably need 3 or 4, right? But you can get started on the basics, and a lot of stuff you can just dig into and discover yourself. What do I mean by being event-driven? So when we talk about messaging, we're really talking about an asynchronous interaction between two apps. The trouble with asynchronous is that you will tend to think of async await. The thing about async await is it's not really asynchronous, right? So what async await does is it says, okay, I'm going to give up my thread to you, and you can do something more useful with it until my I/O completes, and then I will get the thread back. And that isn't really a good description of asynchronous in terms of inter-process communication. So when we are synchronous, which is the left-hand side, when we are synchronous, then typically we assume that both parties to the conversation are present at the same time. You send something a request, it gives you the response. If it's not there, it's down for maintenance, it's crashed because of CloudFront, then essentially your conversation will fail. So synchronous conversations have a dependency on the uptime of two processes. And typical things like OpenAPI, GraphQL, gRPC, Thrift, SOAP, these are all synchronous communication protocols. But an easy way to think about it is it's a phone call. If I phone Dylan and say, in order to try and arrange a night out, and Dylan doesn't answer the phone, it's a failure. I've got no beer, right? And no night out. So that's one of the problems with relying on HTTP, gRPC when we build larger systems, is that synchronous interaction. In an asynchronous conversation, both parties don't need to be present at the same time. And the way we achieve that is effectively a mailbox, right? I send you a message and it sits in your mailbox and you can collect it whenever you feel like. The classic American mailbox with a little flag is a good kind of conceptual metaphor. But you mostly, I suspect, when you're organizing a night out with your friends, tend to rely on using a message app, Signal, WhatsApp, etc. And you do that because it used to be very frustrating otherwise, right? You would effectively keep playing phone tag with each other. You'd never succeed at the communication. But now you just use a message. The person's going to pick it up when they're good and ready and they can deal with it. And that is effectively why we want to use asynchronous conversations, because they give us that level of resiliency that both parties don't need to be available at the same time. That's why we refer to it basically as eventual consistency sometimes, right? Eventually, the other side will pick up the message and work will get done. Now, one tip on that, when people hear eventual consistency, they hear slow. Messaging can quite often be faster than a classic HTTP request response. We do not mean slow. We just mean that there's a guarantee that eventually you will come into line, which there isn't with synchronous. So I mentioned file transfer. So file transfer, right, is this really old school mechanism where effectively, back in the day, it started on a mainframe where I only had one program at a time, right? So I effectively load my data into the program, run it, spit it out to another tape, and then effectively load a new program on, take that output tape, and keep repeating the process. And we often use that even today with accounting platforms that require, for some reason, though, even though it's 2025, that I write everything to a CSV file in a given bucket where the accounting platform will load it from. And while you may think, oh, that's antiquated, given the unfeasible reliability of S3, it's actually a very effective way of working is to write something into an S3 bucket because it's probably pretty safe there, right? And then have something else pick it up afterwards. And the only thing is that as you begin to work with that, you have to think about things like, well, hang on a minute. If I've got multiple readers, how do I do locking? If I've got a lot of work, how do I signal that work is available? And really, messaging is just solving all those problems you get with basic file transfer. It's just doing it for you. In fact, Kafka is an append-only log. It is just a file that you write to, right? So it's just fancy file transfer. Why might you use it? So here's a very typical usage of messaging. It's a task queue. Anyone familiar with the idea of a task queue? Few heads nodding, yeah. For Python people, this tends to be something they really understand quite intuitively because they tend to use Django along with a product called Celery, and Celery is a task queue. And the idea is that when I receive a web request, rather than effectively immediately processing it, what I do is I just acknowledge that you sent me a message and I put it on a queue. And what I'm doing is I'm saying, okay, the hard bit is the work I have to do in response to that message. I don't want to tie up a thread on my web server doing that. So I'm going to put the work onto a queue, freeing up my web server to use that thread to go and basically bring on more work. And this work is now in the queue. If it's in the queue, it's safe. It's stored to disk probably, and essentially if things crash, someone will eventually get to the work. And at the far end of that, I put another application that essentially reads from that. Now, channel is just a generic term we use for things like stream or queue. So we're just going to say channel for now until we know what stream and queue are. And we say basically, okay, I'm going to read from the channel, and then I'm going to basically do my work. And one of the advantages of this is throttling. If I get a sudden surge of traffic to my website, it doesn't matter, because effectively I can just put all that work on the queue. I won't overwhelm my database if it's got some DB connection pool, because I can consume at a given rate, which eventually means I won't overwhelm the database, right? So I have had to explain this to quite big, since I've been working at Just Eat, delivery providers, because we overwhelm them when effectively, and they give us back 503 bad gateway errors, and we say what happened, and they say, oh, we ran out of connections in our DB connection pool, and we say, let me explain to you the magic of task queues. So task queues work because obviously, as you all know, HTTP has an asynchronous option. We know what that is, right? What do you return? You've seen a spoiler. Anyone know what do you return from the spoiler? 202. 202 basically says, I have got your message, right? And I'm going to do something with it. Thanks very much. Okay. So people often wonder when they're interacting with message systems, how the hell does it work asynchronously if I've got my HTTP request? The answer is you can be asynchronous on your HTTP request, right? Queue a work item, etc. So how do I know that that's going to succeed, though, right? I get no response back. It's all asynchronous. How do I know? How do I tell my customer your food is on its way, right? So the answer is that basically HTTP has a location header. And in the location header, you say, where should you go to find out about this piece of work that you gave me? And you get a couple of options. The most common option is just to give the URL of the resource that's being created or like, because typically you're doing an async response to a post, maybe a put, where effectively you're saying, hey, I want an asynchronous response back to this. So typically you say, well, this is where the resource, this is the URL of the resource, or until it's going to give you 404 until you're done. Some folks don't like that because it's kind of like, well, 404 might go on forever. It might never be done. How would I know, right? So what they want is some kind of progress page, and you effectively hit the progress page until essentially it is done, and then you get a redirect, and that takes you to the actual resource. Right? So if I've got a progress page to update, typically the way I do that is the backend app or whatever is processing it effectively updates something like Redis or a similar key value store saying, okay, here is the progress on the job. Everyone keeps updating that based on an ID in the header of the message. And the URL just goes to that particular row in the KV store, finds the data and says, okay, here is progress. We are currently reticulating the splines, whatever fancy message you want to give out. All right? And that gives you async. Basically controls and manages your load. Obviously, Cloudflare has struck again. Does it sort of just warm itself? Wow.
That's interesting.
So the lemon slide is not part of the plan. It's not some sophisticated.
Maybe task is being performed and we are seeing.
Yeah, we're in asynchronous operation right now. It's a demonstration. Have I stepped too heavily?
It's been cursed tonight. The setup that normally works decided this was the day it just wasn't going to work.
Do you want me to plug and unplug at my end?
I can see. I have trees. Just for a second. What have we got coming down the other end? We got trees.
That's my. What it may have done is switched to out of it's done your favorite PowerPoint thing, and switched the mode. Let me stop this presentation. What happens if I play from current slide? Oh, I see. You just want to be on that one, do you? Okay. Well, that's interesting. Let me just see if I can find this. This is the bit where we go, I need to find the settings which live on there. And then say to it, extend my display. Okay. You need another copy? No, you're going to make me find out where that extends my display over here. Displays. Arrange. Side by side, that's entertaining. What do I want to use as main display? How about mirror? All right, when I got it on both sides now, let's see. That looks better, doesn't it? Okay, that's a bit weird. Hang on, I'll put the mic down. One thing that's decided to hide from us is PowerPoint. Let's start PowerPoint again.
PowerPoint has a special feature where it puts itself on an invisible monitor and then deletes it.
Yeah, that is a bit of a thing, right? No. Yep. Yep. All right. So the way you may think about messaging more is what I would term a reactive architecture. So I tend to use the term reactive rather than event-driven, just because, as you'll see later, the word event is itself so overloaded it gets confusing. So by reactive architecture, we mean workflows along queues or along channels between components that essentially transform that work in some way. You can think a bit about the Unix command line where you can pipe stuff together. So the idea is if I am, got a basket that moves to payment, that moves to fulfillment, that moves to a courier, I'm transforming the work as it flows through. That's what I mean by reactive architecture. So in the first scenario up here, what we're effectively saying is I can use a message on a queue typically, to invoke an operation in another application. So I say, hey, please go and do this for me, take a payment. And you can see that effectively, if you keep looking on the left-hand side, it responds to me over another channel. That is because messaging is unidirectional. You want to think about it like a river or a stream. You drop things in one end, right? So when you're playing poo sticks, you drop it on one side of the bridge and it comes out the other. If you drop it on the far side of the bridge, you're either cheating or an idiot, right? And so it's the same is true with messaging. Things flow one way downstream. So if you want a response, you need a separate channel. And the way you figure out what basically is the response to what I sent is you have a correlation ID, just like on a letter where you have your reference. So you give it an ID. And so when you get the response back on the channel, you can go, okay, what did this relate to? And typically what that means, because you are asynchronous, right, is that you may have to save state between the call and the response getting back. So if you had an order and you're saying, well, I need to take payment for it, you send the message to the payment service takes payment, message comes back saying, here is the payment for this order. You look up the order and you advance its state machine to say, that's now paid for, right? So that asynchronicity requires you to be able to save state while you're waiting for an answer. You don't have to go to sagas, right? Some people persuade you sagas, they answer everything. You can do that quite simply with a tiny little state machine or an aggregate or whatever, or just a simple enum that tells you the status of the value, right? So don't overcomplicate your life too early. The other thing that can happen is, so this is basically the left-hand side is showing you basically I am creating a command and I'm getting some kind of acknowledgement or response back. And on the right-hand side, what we're saying is you can also publish a message to a set of consumers to tell them something happened. So here, maybe what I want to say is, oh, that order got paid for, and all these other people may be interested in understanding we now have a paid for order, so I'm going to distribute the message to them, right? So there's these two kind of things we're doing. One is I'm invoking an operation and typically getting a response. Sometimes I can be fire and forget. I don't need a response, just go and do the thing. And typically if I do that, it may be just go and do the thing, only tell me if it goes wrong, right? Or I can publish and say, hey, everyone needs to know this. We will come back to that topic. Okay. Producers. So producers are what we use, that's a term we use for you are sending a message, right? The diagrams are tiny, but they don't show you that much anyway. So the top one, we can use a queue, and we can use a queue to address usually one other application. So we say, here is something for you, right? We'll come back to the characteristic queues and streams several times during this presentation. So we're going to build your knowledge to understand the differences between them. We'll start easy. A stream, we're saying effectively, hey, many people might want this operation. So here I'm publishing some kind of fact. So everybody gets to read from that stream, right? Everyone reads from the same stream. So on the top one, you can see, well, we're thinking particularly about invoking an operation, which we saw on the previous slide, right? This idea of invoking an operation that you have. Potentially, I've got a response channel. And the bottom one, I'm thinking about publishing a fact. We complicate the picture a little bit by having a broker. So a broker says, I'm going to give you some kind of routing, typically. And I'm going to route a message that you send to one or more queues or streams. It's just a way of tying those two things together. The cleverer amongst you will notice that there is a little bit of confusion there between, well, I send a message to a router and it sends it to 5 queues, which applications then need to read, or I publish down in the bottom left-hand side to a stream, which everyone reads. So why is there a difference? Right, we'll come back to it. We typically say channel as an abstraction of a queue or stream when we mean a messaging thing that sends basically a virtual pipe between two applications to save us having to say queue or stream and have to figure out which one it is all the time. All right, so we'll dive straight into transactional messaging, which people usually leave for a little bit, but I think it's very important that you know. So when I send a message, typically, I may well be sending a message in response to the change of the state of some entity that I own in my application, right? There is an order and I'm ready to take payment for it. I'm going to send a message. The state of my order is pending payment. The problem that we have is we don't have a transaction provider that spans both my database and that channel. Once upon a time, in the dim, distant past, MSMQ and SQL Server, you could use MSDTC to span a transaction between them, right? And so you could use transactional messaging to do that, and then you built something called End-Service Bus on top of that particular idea, right? But nowadays, we don't use that combination of technologies together that frequently. So typically what we say is, okay, there has to be a different way of me ensuring transactional integrity, because the problem is if I fail to send the message, downstreams may not be consistent with me about the state of the order, right? I think the order is pending a payment. No one downstream is trying to take that payment. This is going to be stuck there forever, and the customer is going to complain to our helpline, or more likely with our customers, go onto Reddit and write an angry screed. Alternatively, if you did it the other way around, you said, I'm cleverer than that. I'm going to basically send the message first and then update my entity. The problem is downstream is going, I'm going to take a payment for that, but you upstream are going, I'm not even close to taking a pending payment. Why is this message returned saying that you've taken a payment for me? There's something gone wrong, right? So you need some way to correlate these two, all right? So basically we do a trick. We say, okay, but I can have transactions in the database. So what I'm going to do is write 2 things to the database, the change to the entity and the message that I want to send. Typically, we often call that the Outbox table. We call the whole process the Outbox. But the idea is I'm writing the message that I want to send to basically the database. And then a separate sweeper process is what we tend to term it, will effectively iterate through the messages that have not been sent and attempt to keep retrying to send them. And the idea is what we call guaranteed delivery. Eventually, I will send that message. Whatever problem you had with that channel that you couldn't talk to it, doesn't matter. Eventually, I will send it. And there is a slight catch. And typically that is that what happens is I write to the Outbox and I say, okay, it's pending being sent. And then you, in my sweeper, go and send it. There's no guarantee that effectively you won't crash before you have updated that Outbox to say it was sent. It's not common, but it could happen, right? Now the thing is, that's fine. You failed to a safe condition. It's just still not marked as sent, and you will send it again. But that does mean that we refer to guaranteed at least once delivery. What we mean by that is you may get duplicates, right? So we don't talk about too much in this talk, but typically what that means is you either have to be idempotent or downstream, you have to look for things you've already processed and YOLO them out of existence. Right? So typically I refer to that as an inbox. You have to have an inbox to check the key. Someone was asking about this before the talk came on, interestingly enough. Okay. All right, so I'm going to show you some code. We will actually run the demos. There's a demo section later, but I'll just talk about code for now. I want to build up the whole idea before I show you a demo. So I got bored with writing demos that were hello world, so I decided to build a transmogrifier. So anyone who's so young they don't know who, you've got no idea who Calvin and Hobbes are? Yeah, no, either no one wants to admit it or you're old enough. So. All right, so Calvin and his imaginary, lives in the world of his imagination, along with his tiger Hobbes, or Tommy the tiger, apparently, if you're in Scandinavia. I had to learn that for doing this talk in Scandinavia. But he has a box called the transmogrifier. And in fact, on the outside, it has a dial, and it lets Calvin turn the dial, put the box on his head, take the box off, and he's been transformed into like a tiger, a dinosaur, an eel, a worm, whatever Calvin wants. So we're going to build a transmogrifier. That's what you'll see the examples referring to. We'll actually run one at the end, where effectively we're going to ask who you are, what you want to be transformed into. That is going to be our message. We're going to send that over the wire. And on the receiving side, we will transmogrify you, and we will see the output. It's just slightly more exciting than Hello World, okay? All right. So I'm going to talk about Azure and Azure Event Hubs, just because often .NET devs are in this space. It's not entirely dissimilar if you're an AWS, where you have basically SQS and Kinesis, right? Or you may be using NATS or whatever your preference is. But the principles of this are all pretty similar. And you can just go and use an off-the-shelf framework rather than write all this boilerplate yourself. So how do I produce a message in C#? So this basically is my transmogrify operation. And for my transmogrify operation, obviously, I need to send a message. So you can see that the first thing I'm going to do in line 8 is I'm going to write the message that I want to send to the Outbox. Now, I'm not actually saving any data about the transmogrification in database here to try and keep the number of lines of code sane. So there's no actual transaction here, but you would either usually create the transaction, pass it into your Outbox, effectively so that it would add its basically right to the Outbox, and then effectively change your entity, etc. Or you just add an Outbox table into Entity Framework Core, or your life is much more complicated and you produce a generic framework like Brighter, and we have to do fancy stuff because we don't know what you really want to do. So right to the Outbox, and so my message is in there. That's the message I want to send. So effectively now, if I basically fail, it's okay. It's in the Outbox, sweeper will pick it up. And my message effectively is then turned into a service bus message, right? There are different ways of doing this. I could have written the service bus message to the Outbox if I wanted. Typically, I tend to write my intent about the message, but you could write the service bus message yourself if you want. So that is the transport specific, we would tend to refer to that as. So a service bus is our transport or a piece of middleware. So we convert it into that message. It expects those protocol. So Well, taking transformation is just basically our data. What is the transformation? We have message ID, subject, and content type are basically cloud events headers. Typically, subject actually probably should be more like transmogrification, but we'll ignore that. I can then add some additional header values. That can be quite useful to me. When my message created, it's quite useful to be able to diagnose problems. And I'm adding the name. So I'm actually cheating a little bit and piggybacking the name of the person who's being transformed in metadata, which you probably shouldn't do. And then what I do is I mark status. So I say, it's now been sent. Right. Now, if it crashed before that, again, what would happen is it would just be resent. So you would get a duplicate. It's a fairly sort of simple version of how this works, right? I've got no exception, error handling, anything else, just the simplicity. But that's all there really is to it, all right? I just turn my message into the protocol's message type, and I've basically called send async, and I've wrapped the whole thing in an outbox for safety so that essentially I can resend it, all right? So this is basically some of the header information from that dispatcher. I'll show you the code and ID at the end. You can see that effectively we're able to set up some retry options. So typically you want to do some kind of immediate retry before you let things fall over to the outbox, because that'll reduce the latency. The outbox only run every so often, and that is latency that you're adding to the receipt of the message. So typically we do a little bit of retry. And then sweeping, which is a bit harder to see. So we want to basically have something in the background that will pick up any messages that we haven't sent. So we're just going to create a timed background service. Now, you don't want to create a timed background service necessarily. Well, you may want multiple sweepers in production, because one sweeper is probably going to be bad when it falls over. You don't necessarily want to have your sweeper running inside the same code as your producer. But the principles of what you're doing will look very similar in your sweeper code. If you want one sweeper, obviously you realize I need some kind of leader election so that only one of my sweepers is running at once. You may go to your boss, it's time, I'm going to implement the Raft protocol in .NET. Don't do that. You can do something simple, like what we call a poor man's distributed lock, which is basically write a row in a database and say, I've got the lock, and give a timestamp when you were there. And effectively that timestamp is too old, someone else can steal the lock from you. All right. Or you can take a lock off S3 or Azure blobs. There are plenty of ways to do what we call a poor man's lock. All you're trying to do is get one running at a time. That's why Kafka used to use Zookeeper, basically. And then effectively what you want to do is say, well, are there any messages that are outstanding? So typically you have some call, which basically says, go and look in my outbox, which messages haven't been sent within a certain time window. So you typically want a time window. If you're going to do what we call an immediate send, in other words, I'm going to send in my transmogrifier to basically try and get it out the door, and I'm just using the sweeper as a backup, I want to leave quite a bit of time, because typically I hope it's been sent. Some people don't do that. They just say, I'm just going to store everything in the outbox. Sweeper's going to do all the sending. And in that case, effectively, you may want to make the interval of the sweeper a bit quicker. So you get your list of available items, and then really what we're doing here is just essentially the same process we did in transmogrify async, which is take our transformation message out of the outbox and then send it via end service bus. If we have an exception here, we're showing exception code just because typically we can just ignore it. We just ignore it and move on, because a next good sweep may well get the message out and send it for us, right? So fairly straightforward. Outboxes are not a super mystery. You may want to rely on, frameworks because they know how to do it at scale, but it's not a huge mystery. Okay. Azure Event Hubs. So Azure Event Hubs is the streaming option. We're going to explain streaming queues in a second, but it's very similar, right? So here, effectively, what I'm doing is I'm saying, okay, add to the outbox. Then for Event Hubs, I create a batch, because essentially it's more of a streaming operation. So typically maybe batching up work. We're just going to have a batch of one, so we're cheating a bit, which kind of implies we probably didn't need really Event Hubs. We're going to send the batch, right? And then we're going to mark it as basically done. So very similar, deliberately so, by the Azure team interface to work with. Again, set up and basically add some retry options, etc. Right, and then flipping a message again, very, very similar. Find the list of pending messages and essentially iterate over them and send them. We could, in this case, actually use the batching, right? Because we have an actual batch of work that we are reading out of the Outbox. Okay. So we talked about both Service Bus and Event Hubs. We said that one is queuing, the other is streaming. Mentioned that a few times before. I'll give you a few more clues as to how we figure out which one we use. So one thing is we talk about messaging versus eventing. And there are, depending on the people talking to you, they may be being very specific or they may be being very loose. You can't guarantee just because somebody says messaging or eventing what they mean. So you do need to drill down a bit to understand if they are being semantically strict. So a message has intent. It is something that I want someone to do, right? It is me saying to Dylan, buy me a pint, right? And eventing provides a fact, something that has happened in the past. Typically for a fact, you want something like, I now have a pint, right? Be very wary of what we call passive-aggressive events, particularly as you are British, you may well fall into this trap. Because, yes, the Ian is thirsty problem is very common in event-driven architectures, right? Because you go, I'm loosely coupled, I have eventing, I'm just issuing an Ian is thirsty message. But you're not, your boss, you're not going to be that happy if everyone goes, but you didn't say you wanted a pint, so no one got you one, right? You're going to be like, Mr. Grumpy, right? So that's what the problem with passive-aggressive, right? So it's just semantics, mostly, so just be accurate about what it is you actually mean. Typically messaging, we do something like request and answer, right? So that's a query if you think about it. Transfer of control, hey, you've got this, here is a command. We maybe command acknowledgement, which basically is, hey, you've got this, please do something for me. Oh yeah, I did that thing for you, here it is. Transfer of value is effectively more, hey, you've got this and I'm not interested anymore, right? That's you. Eventing is more a report. Hey, this thing happened, maybe somebody cares, and it has no expectations about what will happen. Messaging is typically part of a workflow or a conversation. So you are trying to get some work done and you use messaging to say, hey, please do this for me, please do that for me. It's structured, you know what you want to happen. Whereas typically eventing is history and it's providing context for future action. All those of you who sit there going, I just use Kafka to do everything. Yeah, that's not a good choice. Messaging is concerned with the future, and eventing is concerned with the past, right? The way I think about it a little bit is stuff on the left, you can think about saying, you have some kind of interface, API interface that you expose, and I can call it, and my message is effectively the parameters to invoke in that operation. The one on the right-hand side you can think of as I am just pumping stuff out in a stream. It's a bit like giving you access to my database, only it's much safer. There's old school terminology, which you will still hear a lot, which talks about messaging being a command, eventing being an event or notification or a document. Event is just skinny, document is fat, right? The reason bit for the changing is obviously a command could be a query here, right? So calling it commands means people go, yeah, I can't do that for queries though, can I? Right? And you can. Okay. Consumers. So the key to what consumers do, which is essentially the other side of the equation when you want to read a message, is called the message pump. So in the message pump, we do a number of things. The first thing we do is we get the message. So we need to get the message off the queue or stream, read it off. Having got that, that is basically a message described in the protocol of the middleware that we are using. So we need to turn it into something we can actually work with in our application. If it's an order embedded in the body, we want to turn it into an order. If it's essentially a delivery request, you want to turn it into a delivery request, right? If it's an insurance claim, you turn it into an insurance claim. So we translate the message. To translate, you need to serialize, or you need to deserialize whatever the contents of that body is. And then we dispatch. So something now needs to deal with that message. And we say, okay, find something that can handle the message of this type. And then, tell me that we're done. So that is the handler. Pretty much a large amount of compute that you use day to day works this way. Any Windows systems that you have, be it Mac or Windows or whatever, uses basically a message pump, sometimes called the event loop. Right? It's a fundamental idea in computing. I've written WM proc in C++ many years ago, which is a fundamental message pump, which is also the single-threaded apartment. So then if you've seen STA thread in basically when you're working with .NET for COM interaction or something like that, an STA thread is a message pump. That's why also all those restrictions when you're using, say, Windows Forms about calling thread or not, right? It's all to do with message pumps. So if I don't get the message, then what I'm going to do is put it on what we call a dead letter channel. So I'm going to say, okay, we couldn't deliver this message. In other words, we couldn't read it off the messaging queue successfully. I'm going to put it on a channel so somebody can investigate later. If I couldn't translate the message, in other words, I could get it off, but that I can't deserialize it properly, technically, we should put it on an invalid message channel. Most of us cheat and just write to the dead letter channel, but technically you would want to. Typically, that may be a good message, but it's just either you don't understand the version or someone's done a configuration snafu and you're now being sent messages meant for another part of the platform. So typically you want to try and put those on some dead letter channel or the like, because probably there's some work there that needs to get done by somebody, just came to the wrong place. If you can't dispatch, your software is configured incorrectly, log and crash. If you can't handle, you need to understand what type of error you have. An unrecoverable error is one that no matter how many times you try this, you will not succeed. In that case, simply log that as an application error. Okay. It doesn't go to the letter channel. It doesn't really go to the error queue unless you like beating yourself with a stick, because somebody has to basically write something that goes and reads the error messages out of the error queue. And it turned out that you had a perfectly good mechanism for dealing with application errors, and that was effectively logs or traces, right? Don't make your own life hard. Just it is a typical application error. It is unrecoverable, so you just log the error. We're not going to retry at that point because it would never succeed. That's what we call a poison message, because effectively you can't make it work. If it's recoverable, in other words, timing is the issue. Either a resource you need to process that message is not available, or potentially it's out of sync. So that could be, hey, that database I need to talk to is suddenly on the fritz and it's giving me errors. But I'll retry that again a bit later. Hopefully the database will get fixed. Or in an eventually consistent system, the customer bought an item in product catalog version 13, but when I look in my lookup table, which is a whole bigger issue we won't get into tonight, of for catalog data that I want to match up against the order, I only have version 12. Okay. Probably there is an incoming message about to update you to version 13. You just haven't got it yet, so you requeue and give that time to all basically come back into sync. So that is effectively when you have a recoverable exception, you effectively requeue. Typically, you requeue with a delay. Not all messaging middleware supports requeue with delay. You may again want to rely on a framework that basically has some scheduling facilities. Typically, you also want to have a limit where effectively you say by policy, hey, requeue this 10 times, and then move it to the data channel. In other words, give up at a certain point because maybe there is a poison element to this, even though we thought it was recoverable. Okay. You may also need some things like a message mapper registry to help you do the translation, a handler registry to look up the handler. Okay. So at the top, you can see a queue, and the queue effectively has the letter channel. We consume from it, and if effectively the event we fail to queue, we write to the letter channel in the event that we basically can't process that message successfully. Okay. On the bottom, we have a stream. Streams do not have dead letter channels. Many people's first thing when they get hold of Kafka is, there are no dead letter channels. We must write dead letter channels for Kafka, right? The reason it doesn't have the letter channel is because streams are immutable. They're just a file, right? Remember? And they are immutable. You as the reader can't change them. So the work you could not process is still on that file. There is no need to copy it somewhere else. The only thing you need to know is what are the identifier, what is the ID of the message you could not process, so you can go and look at it later. Copying it to the letter channel doesn't actually do anything for you. You just need to go and look it up in a different queue with that ID, which is kind of the same thing you could have done in the original channel. The most common request we get on Brighter Ready for Kafka is, why don't you support the dead letter channels? And then Ian explains why you don't need dead letter channels. And then they go, yes, but mass transit has a dead letter channel. Why don't you have dead letter channel? So announcement tonight, we're probably going to do dead letter channels for Kafka, even though it is insane, because the world is just awful. You know better though, right? You know why you don't need dead letter channel. We'll explain a bit more. Okay, queues. So now we're going to get into queues versus streams and do a little bit of information for you. Okay. So a queue, when I basically read a message in a queue, what I do is I lock that message. I say, Bagsy, mine, I'm processing it, right? Nobody else gets to do that. So if a second queue comes along, they do what we call read past. So this whole strategy is called lock and read past. So read past, it says, oh, somebody else has that. I'm going to read the next item in the queue. So it gets the next item and the queue, and it locks it. Notice, with queues, you are not ordered. Right. You can get things called FIFO queues, which kind of basically lock everything with the same message, with the same group identifier. You can do that. Really, the question is, should you have a stream? But effectively, you just read the next item in the queue. And that's quite powerful, right? Because it gives you a way of doing scaling, but your goal is to treat these things as independently processable tasks. Okay. Once I have effectively finished with that piece of work, I unlock it. Usually I've finished processing it successfully, in which case I ACK. When I ACK, it is deleted from the queue. No more, no one gets it, I'm done with it, right? I don't want anyone else to do that task because that'd be doing the task twice and that might have bad side effects. So we're going to delete that task right out of the queue. If I fail, it may be that I fail because I say I'm going to requeue with delay, or if I fail because effectively I crash, then what tends to typically happen is we basically want to put it back on the queue after a timeout. And that timeout mechanism is just a lock. So we just lock that record for a window of time to say, okay, no one gets that one until the timeout passes, or effectively we realize that you've crashed as a consumer, and then we'll stick it back on the queue. So queues can scale what we call competing consumers. In other words, I can just keep increasing the number of consumers that I've got to basically eat work at the queue. I won't get into queuing through tonight, but basically imagine that it's a busy bar and you've got to figure out how many people serve the customers coming in. That is basically what queuing theory is for. It was written, I'm sure, by mathematicians to figure out how they needed to staff the bar, right? But that's competing consumers, right? Streams. Streams are doing a second, yeah. So Azure Service Bus is a queue and consuming a message, basically. You can see what we're going to say here is we've got passing in two delegates, one to translate and one to handle. So those are those parts of the message pump. If you look on line 1, it's just a big while loop that spins it forever until we cancel it. That's basically what a message pump is. It's a big while loop that spins. We're going to call a function to translate and a function to handle, so we can have a generic loop that we can reuse. And if we get a success, we're going to basically say, yay, ACK, delete that thing from the queue. If we fail, then we may choose to knack, to hand it back deliberately. If we crashed, it would just knack in the end itself. All right? So you can see here us using that queue. Don't worry about all this vector console stuff, but what we're doing is we're saying, okay, run the message pump. Effectively, the translator says just create a transmogrification out of the subject and the body string, right? That's what we were sending earlier from the producer. And in the handler, I'm just going to use those values to do some work. And at the end, because I've succeeded, I'll return true, and the work is deleted off the queue. Right, streams. So in a stream, right, I should read the first message. My arrows are slightly out, ladies and gentlemen. They should be both pointing to the same message, but there is no deletion. So what happens is every thread that you pointed to stream begins at 0 and starts reading every item. The way I think about streams is I've effectively got a file and you're calculating doing the old school, what is the offset into the file at which I should read, and because you know the length of a record, and you just keep incrementing your way through it. So when you have read, you record the offset. How far into this file have I read, so that if you crash, you can resume, but every thread you add starts at 0 and works its way through. So if you increase the number of threads, you aren't going anywhere, right? So how do you fix that? So what happens is basically partitions. So we partition the topic into multiple partitions, right? And then effectively you read not the whole topic, but a partition on that topic. And the idea is you guarantee that anything that effectively has the same identifier will end up on the same partition. And typically you use a strategy called consistent hashing, which means for a given ID, I'll always end up in the same bucket, right? And therefore each thread just reads one partition and marks its offsets. Consumer group is because I may have multiple applications that all want to track across their own offsets. So that is queues versus streams. Azure Event Hubs is a stream. And Event Hubs, because we're dealing with basically partitions and you may be given and granted and revoked partitions, typically we are using the off-the-shelf event processor, which effectively internally has a message pump. So we're not saying message pump here. You can write that yourself. It is a bit complicated. So typically what you're doing here is saying, okay, I'm setting up basically a process event handler, a process error handler, which essentially is what I will use on the processor to react to messages that I receive. And if I process successfully, what I'll do is do my translate and handle, right? And then I will update the checkpoint to say commit, effectively update the offset that I have read to. And if I get an error, I will just basically pump that out and I won't necessarily increment my offset. You can, in some cases, decide I'm going to increment the offset and say, you know what, I'm going to give up on this record, even though basically I didn't successfully process it. And a little bit that depends on how badly do you need to read all the things in order. There are ways around that. We haven't got time to talk about that tonight. All right, skip that bit. We can come back to that when we do a demo. Here's what I want to show you. Messaging, basically, then, and events. So messaging basically is typically over a queue, not a stream, and events are typically over a stream and not a queue. Do not worry about the response to a command acknowledgement. Just treat that on the same thing as a message. Right. Okay, quick demo. They're recorded, so it all should be good. I'm just going to... So the code is available on my GitHub. I'm not going to delve deep into it because me flashing lots of code at you won't really help you. But basically, there's an ASB demo and an AEH demo, and effectively, you can see there's a dispatcher. That's all that code that does the producing. We were talking about transmogrify async, and the other really interesting bit is in the consumer. You can see that there is a message pump, which is doing that key piece of work. And there's one of those for AEH and ASB, right? So I invite you to go and look at the code yourself. It is not production code. I don't think anyone assumed it was, but I always have to kind of say that just in case. All right. Come on. All right. So what we're going to do is set up the transmogrification. On one side, we're going to set up what we want to do, right? So we ask what your name is. You're going to be Calvin. We basically ask what you want to be transformed into. Calvin's going to choose to be a tiger. And what we're doing is sending a message. And at basically the end of it, we're going to pump out some information saying we added this message to the outbox with a pending status, all right? And then we mark that we sent the message, and then we mark the message as sent in the outbox. And we're done, so we'll move over to the other side. Right, and what we may show you in between, I think, yeah. So we go and look in a basically Azure Service Bus. We need to refresh it. It will show us when it refreshes that we have a message waiting. So we are asynchronous. That would wait there for eternity. Well, probably until Microsoft basically goes bust when the AI bubble crashes. But it would wait there at least that long for us to basically consume it. So we can take our time in between doing that and then running the consuming side, where again, we'll just do .NET Run, and it will tell us, begin the transmogrification, and effectively it says, okay, we turned Calvin into a tiger, right? And message is complete. All right, okay. It's just going to show me that if you refresh this, the message will have vanished, right? Because we've consumed it, we've hacked it and killed it. All right. Azure event. How am I doing for time after the demo, Dylan?
You've got about another 5-10 minutes.
Okay, cool. So let me
Just 5.
All right.
The thing that might get us out of here by 9:30, and it's 7 minutes past. So.
Okay, no, that's good. Hang on, I'm just going to go back to the beginning. Go back to the beginning. Okay, there we go. All right, so similar to transmogrification, this time we're basically using an event hub. Here we're going to basically just say very much the same thing. You won't see a huge difference because essentially it's exactly the same code. I may choose a different name if I've been really exciting. I can't remember how exciting I got at this point. David, wow. And what's David being transformed into? A bug. Okay. And there you go. And then, we're going to show you that there's an event hub. We may show you there's an event hub with a message. It takes a few seconds to talk to the event hub. And you can see I've been working through a few times, but you can see the bottom one is David and the bug. It's a stream, so I'm not deleting them in between. So it's never going to go down, right? That's all the ones I've been doing in testing. And then effectively do a run, and you will see David being transformed into a bug. Poor old David. All right. So that is basically sending and receiving messages. Okay. The rest of this stuff is a bit of a stop tour of a few topics. Okay. Types and filters. So messaging, it doesn't necessarily have to be sender to receiver, as we've shown it up to now. Sorry, John. Typically, you can think about Unix command line style, where effectively you push something in between source and sink through steps that happen in between. So here, what we're doing is saying, hey, the first thing I want to do is translate. So this quite often happens when you have different versions of the message being understood by different parts of your system due to legacy reasons. So you may translate it into a new type of message. Enrich, basically, a content enricher says the message doesn't contain all the data that the receiver needs to process it. So I'm going to give it to something else which will add that data in, and then effectively that goes to the receiver. Typically, the translate and enrich may be running as their own independent applications. Sometimes we do this in middleware in the sender or receiver itself, so it's running in memory, depending on your context. If you want to go big with this, you end up with stream processing and applications like Flink, which we use for moving data around enterprises and transforming it on the way in between, right? The Kafka ecosystem is particularly good for data engineering, and it uses a lot of stream processing. The only sad bit is that there are no official stream processing libraries for .NET for Kafka. Okay, there is someone has written one. I don't know how good it is. All right. Splitting and aggregating is also a bit common. I have a large piece of work, like maybe it's a big order that has lots of sections in it which are processed for different parts of my app. I effectively split it up, turn it into a number of smaller messages, bits of my app then process it, but at some point I may need to re-aggregate it to say, hey, I've done all the bits of the order, and you can aggregate it at the end. Typically an aggregator needs some kind of buffer, in other words, something in memory that lets us basically collate all the bits and stitch it back together again. All right, managing. So this is a bit of a whistle-stop tour. I do a talk which you can find on YouTube called Managing Asynchronous APIs. If you want to get into this topic, you can watch that one for this first bit. So this is Async API. Async API is the equivalent of Open API for the messaging world, right? It lets you define your messaging application. It's a very similar syntax. There are plugins for VS Code and other tools and utilities that you know about. This is a schema registry. Why would you want to use a schema registry if you've already defined the schema as part of Async API? You want the schema registry to try and enforce schema. So typically, you'll always do that on the producer side. I would avoid doing it on the consumer side to follow Postle's law. You may get a consumer side if you are building data engineering because you may need to enforce the messages you receive conform to the schema. But typically what happens is you say, here is the schema. I'm going to register it with the registry. When I produce a message, we should check that I conform to the schema. Often what happens is with something like the Confluent schema registry, you can cache the schema locally. It's on your first read, and you can do the check locally, so you don't have to worry if the schema registry goes down. But again, you can go and look into that more. The big thing with schema registries is backwards, forwards, or full compatibility. So it can tell you whether you would break down streams. OTel. So Martin Thwaites and I do a talk about OTel and messaging. Again, you can find that online. Look for the Oslo version. The London version was awful, and you don't want to watch it. Never do a joint talk with somebody who's going to get off a plane at about 6 a.m, 4 hours before you're about to give the talk. It doesn't work as well as you might hope. But yeah, so there are semantic conventions for OTel, for messaging. There's semantic conventions for everything, right? But they give you a very wide event, which is what you want nowadays, in order to effectively understand your messaging. So Brighter V10 does support the semantic conventions of messaging. Middleware and frameworks. So the top row is typical queues. So SQS and Azure Service Bus. SNS is just like I say, a router that effectively lets you send SQS messages to multiple queues, right? Why might you want to do that if you're doing queuing? Isn't that one-to-one invoking? So a typical reason might be you want to route it by country to different endpoints that process it differently. That's kind of built into Azure Service Bus and built into Google Cloud PubSub. RabbitMQ and ActiveMQ are older school ones that were typically built more for data centers. They can run in the cloud, but don't do so well, in my opinion. Amazon Kinesis, Azure Event Hubs, Apache Kafka are streaming applications. Mosquito is MQTT, which is great for IoT and also for doing interop with devices in low reliability environments. We use it. I'm counting in streaming because it works in a similar way, though it's not quite. Things like Pulsar and NATS support both stream and queue. Over time, what is happening is you will see that either the cloud providers provide both a queue and a stream, or for some of the more data center ones, they provide both out the box. Those of you in the know that there is currently a proposal, I think it may be out, but not supported in all libraries, for queues in Kafka, so that Kafka can effectively consume a topic in a queue-like fashion, right? So Kafka will eventually support both. Frameworks. So I'm going to declare mass transit to be COTS here. I probably haven't got all of them, but just a rough divide. So things like N-Service Bus and Mass Transit are COTS frameworks, right? That means you're going to get support, you're going to get people working diligently on it day to day. Things on the left-hand side are open source, although I think Jeremy will offer you a support contract. There's Rebus, Brighter, which is one I work on. Dapper. Dapper is a bit of a strange one. It basically runs as a sidecar over HTTP. I can't remember if it's TypeScript or Go, but that's Cloud Native Foundation. But you can use that quite generically. If you're in a Kubernetes environment, it may be interesting. Just Saying is another one now, Just Eat Takeaway, and that's very focused on being a lightweight wrapper over SQS, SNS. Nowadays, probably rather than Just Saying, even we would say the AWS Messaging Process Framework for .NET does the same job. It's a lightweight wrapper over the SQS and SNS, and you're probably good to use that one if you want a lightweight wrapper. And that's that.